Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we continue our discussion on the small oscillatory motion in this module. We have to begin with another example. This is related to physical chemistry, where we want to find out the approximate motion of a triatomic molecule. So the problem is that of a linear triatomic molecule. Linear triatomic molecule. We see the problem says we have a symmetric linear triatomic molecule. Triatomic molecule is modeled by three particles. Which are connected by two springs. Okay, and we want to find the frequencies of the vibration of these molecules. So we want to find the frequencies of rectilinear vibration of the molecules and the forms of the normal modes. Okay, so the setup is that we have these three molecules. Let's say the molecules are given as follows. We have the first and the last molecules are of equal masses capital M, and the middle one is of mass small m. They are each connected with vibrational strings, which is this form x1, this is x2, and this is going to vibrate with frequency, longitudinal motion x1, x2, longitudinal displacements x1, x2 and x3, right? And now we can write down the kinetic and potential energy. So our T approximate, the kinetic energy will be half mx1 dot square plus half small m x2 dot square plus half capital M x3 dot square, and we can write down the approximate form of the potential energy half. We see that for the middle. Well, so we have to just let us say so our approximate form of the potential energy, these are all related to the strings. So since we have only two strings, we will write down the potential related to these two parts of the strings, right? And let us say we assume that alpha being the string constants, or which is related to the restoration potential. So now we write down the potential energy of the string. So this is going to be half alpha x2 minus x1 square, which is the net stretch of the first string, and then plus half alpha x3 minus x2 square. We are assuming that both parts of the string, they have equal string constants. So now we have that T is half m times 0 0 0 m 0 0 0 m, and we see that V is alpha by 2 times 1 minus 1 0 minus 1 2 minus 1 0 minus 1 0, sorry 0 minus 1 1, right? So T and V is given as follows. We have just quickly written down the matrix form of these approximate kinetic and potential energy. So now we can quickly set up our eigenvector equation. So our eigenvalue equation is of this form. So this is our T double bar and this is our V double bar. So V minus lambda T, the determinant is of this form. We can see that this is 1 minus mu minus 1 0 minus 1 2 minus mu by gamma minus 1 and 0 minus 1 1 minus mu. So this is equal to 0 and we can solve this these eigenvalues. Well, again our mu is related to this constants. We can solve this matrix, this determinant equation. We see that the eigenvalues are 0 1 and 1 1 plus gamma, where mu and gamma, they are all functions of these constants alpha and m, small m. So listeners can go home and check all these constants. They will come out to be the function of these previous constants alpha, capital M and small m, and these are my eigenvalues. Interestingly, there is one eigenvalue which is 0. So which means that the 0 eigenvalue is going to correspond to uniform oscillation, and the other eigenvalues, non-zero eigenvalues, they correspond to the non-uniform oscillations. So what I just said is the zero root is corresponding to the uniform oscillation, right? And the other roots are given by omega 1 square is alpha by m. So this is the corresponding to mu equal to 1. This is corresponding to mu equal to 1. And the other third root is omega 2 comes out to be 1 plus 2 gamma times alpha by m. I think our other root was 1 plus 2 gamma. So I missed a 2 here. So 1 plus 2 gamma alpha by m. So this is for corresponding to mu equal to 1 plus 2 gamma. Okay, so then we can do the exercise. We can find the amplitudes, the eigenvectors for this. The eigenvectors for this, the first one is minus 1 0 1, and the other one is 1 comma minus 2 gamma comma 1, where we can see that in this, interestingly, we can see that the first component of the string has a minus sign while the other component of the string has a plus sign, which means that the motion of the string will be going against each other. So this is going to be anti-symmetric type of a stretching, and where here the first and the last components are of equal signs. So this is a case of the so-called symmetric stretching, right? So the symmetric stretching, where the motion of the strings, they go in the same direction as each other because of these signs. Again, these are quickly done so that the listeners can go home and check these results. They can start plotting these eigenvectors corresponding to these eigenvalues and see that actually the motion corresponds to anti-symmetric and symmetric stretching. So I wrap up this discussion here with this example, and then I come back to again I continue our discussion on this general theory of small oscillatory motion using and look at more theory. So the theory that we have is, so let us go back to another slide. So general theory of small oscillations. So small oscillations. This is part 2. General theory of small oscillations, part 2. So what we now look at now is, in the previous set of few modules, we had found out what are the normal modes and normal frequencies. Now we will look at specific cases of normal modes which are orthonormal normal modes. Or so first let us talk about the orthogonality of normal modes. Orthogonality of normal modes. So are the normal modes orthogonal to each other? The answer is yes, as long as the eigenvalues corresponding to the normal modes are distinct. They are not equal to each other, or they are unique. So that is the standard result in linear algebra. So again, which says the result is in the form of a theorem. So theorem, orthogonality of normal modes. Or eigenvectors, normal modes or eigenvectors. Right? So we will state this result in the linear algebra format. So the problem says suppose K and L are symmetric n cross n matrices, and x1 and x2 are generalized eigenvectors, right? Eigenvectors of K, generalized eigenvectors of K with respect to L, right? They belong to distinct eigenvalues, belonging to distinct eigenvalues belonging to distinct eigenvalues. Then what we have is x1 and x2 are mutually orthogonal. x1, x2 are mutually orthogonal with respect to L, the matrix L, in the sense that x1 transpose L x2 is 0, right? So they are mutually orthogonal with respect to this matrix L, in the sense that this dot product or this matrix vector product is 0. So we can quickly look at the proof of this statement. This is fairly simple. It says, suppose eigenvalues lambda 1 and lambda 2 are distinct. They are distinct eigenvalues corresponding to x1 and x2. So they are distinct eigenvalues corresponding to x1 and x2, which means that x1 transpose kx2 is x1 transpose, we are going to rewrite this. So x1 transpose kx2 is x1 transpose, let us multiply kx2 first, and we see that kx2, since these are the matrices, we have lambda 1, lambda 2 are the eigenvalues. We see that this is x1 transpose times lambda 2 times Lx2. Where are we getting this from? We are getting this from our eigenvector definition, right? So we are x1, x2 are the generalized eigenvector of K with respect to L. So that is the statement we have used it in this multiplication. So now this is going to be lambda 2 times x1 transpose L x2, right? And then what we have is, so what have we got? So suppose, so this is lambda 1 times Lx2. Now suppose, let us look at this multiplication again. We see that this is x1 transpose K, x1 transpose Kx2. This is equal to K transpose x1, K transpose x1 transpose. So we have just rewritten this quantity on the left as follows. So this is equal to x2. We are again revisiting this quantity and trying to see it from another point of view. So we see that this quantity K transpose X1, K and L are both symmetric matrices, so the transpose doesn't make sense on K. K transpose is K itself. So we see that this is equal to lambda 1 times K, it is equal to lambda 1 times Lx1. So that is the same quantity here, and times x2, right? So lambda 1, so that is what we have. Well, there is a transpose on the top, and then further this is going to come out to be lambda 1 times x1 transpose L x2. And so what we have is that since these quantities are both identically equal, we see that this is, if we subtract one from the other, we see that lambda 2 minus lambda 1 x1 transpose L x2, this is equal to 0. This quantity is 0, and so what we have is that this is only the case since L, and we are also given that lambda 1 and lambda 2 are distinct. See, we began with the assumption that both the eigenvalues are distinct, which means that we have x1 transpose L x2, this has to be 0, or x1 and x2 are mutually orthogonal to each other with respect to the matrix L, and that is what the statement is. Okay, so then I am now going to relate this statement, this linear algebra statement, to our small oscillatory theory. So the theory, we come back, since V and T of an oscillatory system are both real and symmetric. The above theorem applies. The above theorem to the above theorem means the theorem that the theorem that we have just seen, right? So the theorem in the previous slide, they apply to the normal mode theory. Okay. So now if my A1 and A2 are two amplitude vectors. So suppose if A1, A2 are the amplitude vectors of two normal modes. They are the amplitude vectors of two normal modes of an oscillatory system. Then we see that they will have distinct frequencies. So if they are the amplitude vectors of two normal modes with distinct frequencies, we are looking at the case having distinct frequencies, right? So then we expect that the normal modes are mutually orthogonal with respect to the T matrix, right? And so this is the case for distinct frequencies, but that is not necessarily true when the frequencies are degenerate. So what do I mean by that? We cannot use the result in the form of the theorem we saw in the previous slide for degenerate frequencies. So result not true for degenerate frequencies. For degenerate frequencies, that is, the vectors may not be mutually orthogonal. Degenerate frequencies. Okay. So what we have is that from here one thing is clearly emerging from this small discussion. A thing is clearly emerging is that if our normal modes are orthogonal, then they must satisfy this matrix vector product. So if my normal modes Aj, j from 1 to n, are mutually orthogonal, then Aj transpose T AK, AJ transpose T AK, this is 0, right? And J is not equal to K here. So these are distinct eigenvectors. And then, so this is my condition for orthogonality. So orthogonality with respect to the T matrix. And now if we were to change it to orthonormal setup, then we have the following. So we are going to now normalize our eigenvectors AJs. So we normalize AJs such that now AJ transpose T AJ is going to be 1. So this is for J 1 to N. So if we normalize our amplitudes, then this is the case, right? So that is what we have. So we can club both the results. So in this following statement, that if we have an orthonormal setup, if we have an orthonormal modes AJs, then they are going to satisfy the following matrix vector product. AJT AK is going to be delta JK. Well, we all know what is delta function. Delta function will be 1 if J is equal to K, and this is 0 if J not equal to K, right? Okay. So that is what we have. So this is the orthonormal criteria. Okay then. So then we have few more results. The first result is in the form of the fundamental result of the so-called the Rayleigh minimum principle. So what is Rayleigh minimum principle? Again, it has something to do with these normal modes and the normal frequencies. Let me write down the statement. The Rayleigh minimum principle. The problem says suppose an oscillating system, suppose an oscillating system S has n degrees of freedom, n DOF, has n degrees of freedom, right? Has n degrees of freedom, and V and T, the V matrix and the T matrix, that is the potential and the kinetic energy matrix, has no degenerate normal frequencies. Degenerate normal frequencies, have no degenerate normal frequencies, and then for any non-zero, the problem says, the theorem says, for any non-zero column vector of dimension n, we have the following function f of x. Any non-zero column vector of dimension n, we treat that column vector to be, we say that column vector to be x. So we look at this following function f of x. This is x transpose v x by x transpose tx, right? So where v and the t are the potential and the kinetic energy matrices, and this is going to be greater than the fundamental square of the fundamental mode omega 1 square. So fundamental mode implying the frequency which is the smallest out of all the n frequencies. So the function, this function of x is going to be greater than or equal to the square of the fundamental frequency. Okay, so and so that is the first statement. The second statement is further the minimum is achieved. The minimum is achieved when x is a multiple. The minimum is achieved when x is a multiple of amplitude amplitude vector. The minimum is achieved when the x is a multiple of amplitude vector, or the so-called fundamental mode. This is our fundamental mode, right? And so I want to show that the minimum is achieved when x is some alpha times a1, where a1 is the corresponding amplitude to omega 1, and alpha is just a scalar proportionality constant. It's a scalar constant, right? So these are the two results that we show in this Rayleigh minimum principle. And the proof of the idea is very simple. We first sort out the frequencies in the ascending form, and then we look at these quantities x transpose vx and x transpose tx and see what happens. So suppose n is the normal frequency which is ordered. So we have n normal frequencies which are ordered, where we have the frequencies being omega 1 less than omega 2 less than omega n. We have n normal frequencies which are ordered, and then we have the corresponding amplitude vectors. The corresponding amplitude vectors being a1, a2, an. So assume these are all normalized. Normalized means that these are all they all have norm 1, right? Their magnitude is all 1, and these eigenvectors are corresponding to these frequencies omega 1, omega 2, omega n, and so on. Okay, so then what we have is these aj's, which are the eigenvectors. This naturally form an orthonormal basis of our n-dimensional space. Orthonormal basis, right? So then let us see what happens to this vector. So which means that we want to find out what is this quantity. This is for any vector x. So now we are going to expand this vector in this orthonormal basis, which is given by aj's. So our vector x can be written in this form. So x is alpha 1 times a1 plus alpha 2 times a2 plus alpha n times an. And now if we were to look at that function f of x, we have to first evaluate the numerator. The numerator is x transpose v alpha 1 a1 plus alpha 2 a2 plus and so on plus alpha n an, right? And then now what we have is these quantities. Let me now distribute this matrix multiplication. We see that this is alpha 1 times x transpose v a1, x transpose va1 plus alpha 2 times x transpose v a2 and so on plus alpha n times x transpose v an, right? van. And now we can further, we know that using our theorem from that we had stated, that linear algebra theorem, that this is also equal to alpha 1 times omega 1 square times x transpose t a1. So that is coming straight from our normal mode, our linear algebra result, and this is alpha 2 times omega 2 square times x transpose t a2 and so on, right? And so on, and we see that the last one will have a factor omega n square. And now we can see that notice this factor x transpose t a1. We can see this factor, let's say x transpose t ak. X transpose t ak can be written as alpha 1 a1 plus alpha 2 a2 plus alpha n an. this is also equal to T times AK. So we see that we have expanded X transpose, and we see that this is also equal to alpha 1 times A1 TAK plus alpha 2 times A2 TAK and so on, and the last factor will be alpha N times TAK. And we expect that this is a standard matrix vector multiplication, and these AIs are orthonormal. We expect that we will have only one factor which will remaining out of these n factors, which will be the alpha kth term. And since these are all orthonormal, the only quantity that will remain out of this matrix vector multiplication will be alpha k. So now we can substitute these values. We can see that these values will be these results we can substitute for the various factors, and we see that Vx V transpose is nothing but alpha summation alpha I square omega I square times well, that's it. So alpha I square omega I square, right? So now what we have is so that is my X transpose Vx. So now similarly we can find out what is the denominator of that function. So that was X transpose T X. The denominator of the function, we can quickly do this using this matrix vector multiplication that we saw. This is also equal to alpha 1 square plus alpha 2 square and so on plus alpha n square. So now we can plug all these results into our function. Our function, let me call this as 1 and this second result as 2. So our function f of x, which we wanted to find, was 1 divided by 2, which is nothing but which is going to be alpha 1 square omega 1 square plus alpha 2 square omega 2 square and so on plus alpha n square omega n square by the quantities alpha 1 square plus alpha 2 square and so on. So this is our f of x, and then we can now remove this equality and replace it with an inequality. If we replace all these omega i's with omega 1, right, and we see that this is also clearly greater than equal to alpha 1 square omega 1 square plus alpha 2 square omega 1 square and alpha n square omega 1 square divided by alpha i's, alpha 1 square plus alpha n square, right, and this is also equal to omega 1 square. So that is the first part of the problem, and of course the minimum will be achieved when we have the minimum of fx is achieved when we have that alpha 2, all the values alpha 2, alpha 3, alpha 4 up to alpha n, they are 0 except alpha 1, and the minimum is achieved when we have that x, the argument of this function x is just a scalar multiple of a1, the eigenvector a1, which means that this only corresponds to the fundamental modes. So that completes the proof of this Rayleigh minimum principle, and we'll continue our further arguments in the next module, the further implication of this result. So thanks so far for listening.